Hey guys, Mr. Ray here. This will be take 2 on the trigonometric functions lesson. It's a bit of a long one, and I am redoing it because the audio on the last one didn't work, so hopefully we're good now. Now, I'm going to try to make this shorter. It kind of got a little out of hand last time. It is a long lesson. It's 8 pages, lots of examples. And normally I would break this apart into a couple lessons, but it just seemed to flow nicely. And if you have, if you want to break this into 2 or 3 sessions, no problem there. I'd rather have you in a good learning attitude and not falling asleep. So, with that being said, so we're going to start off with the basics of trigonometric functions. We're going to be looking at how we transform them into any other shape. We'll talk about the shape as well. Then we're going to be looking at graphing from an equation, and then we'll do the opposite. We'll take an equation, we'll take a graph and create the equation. And then finally we'll take a look at a word problem and just develop first a little graph of it, and then from the graph develop an equation that we could then use to solve other questions around it. So, all right, so let's start off with the main ideas here. So trigonometric functions, they basically come from the trig ratios. So we're going to really focus on sine and cos. We're going to take a quick look at tan, and then the other secondary trig ratios, cosecant, secant, and cotan. I'll just show you what the graphs look like. They're not all that useful. Tan's not that useful either, so I want to really focus on cosine and sine. Okay, so what do these functions mean? Well, if you see this first column here, these are all the angles of the as we go around the unit circle in radians. It's left off 2 pi here, but 2 pi is really the same as 0. So you just get back to where you started. And if you remember, as we go around the unit circle and we have those coordinates around the outside, like 1/2 √3/2, 1, 0. So whatever the y coordinate of that point is for that given angle, that's the sine of that angle. So for example, like the sine of 0 radians is 0. The sine of pi by 6 is 1/2. The sine of pi by 4 is √2/2, etc. So taking this angle and go around the unit circle, first looking at the y coordinates. So I'll just remind you that's the y coordinate. Cosine is the x coordinate, and then tan is the ratio of y over x. Okay, so if you remember, sine starts at 0, goes up to 1, and then in the second quadrant goes back to 0, third quadrant goes down to -1, and in the end it goes back, returns at 2 pi, returns back to 0, whereas cosine starts at 1 at 0 radians, goes down to 0. It's the x coordinate, right? So it's kind of moving left at this point, and then keeps going, goes down to -1, and then starts its way back across to the right. This is the third quadrant, goes back to 0, and then the very end, I might as well fill these values in here. So this would be 2 pi. So it comes back to 1, so basically where you started from again. So these should be very familiar. I mean, they have √2/2 here. So remember, √2/2 is the same as 1/√2. I don't care which way you use. This printout had the √2/2, so that's why it's here. Once we do the tan ratios, we have looked at these for certain angles, but if you remember, sometimes the tan of an angle is undefined, and that's because, well, you have a denominator here. The value x, whenever x is 0, for example, right here, whenever x is 0, you have something divided by 0. That's undefined. Okay, So it's a pretty weird looking graph. You have these undefined values. Okay, now what we do now is we take these, we use the angle as basically the x axis, and the y-axis will be whatever this function, whatever each of these functions are. And once we graph it, you'll see, well, here's the sine, y equals sine of x graph, and you can see it starts off at 0, goes up to 1, goes back down to 0, and keeps going. Now, the thing about these, this function is it keeps on going forever. Every 2 pi, it just keeps repeating itself. So we call these periodic functions because it just keeps repeating over and over. If you look at cosine, you see a very similar looking graph. It just has a different starting point. Okay. Now these two graphs, these are the key graphs. We're going to use these to model all sorts of things. We're going to graph all sorts of transformations of these functions, sine and cos functions. You can see the tan graph here. I'm just going to draw some dotted lines in here. It's hard to see them. So these dotted lines are actually vertical asymptotes. And those vertical asymptotes happen every time we have an undefined value for an angle. So pi by 2, 3 pi by 2, I think. Yeah, pi by 2, 3 pi by 2. If you kept going at 5 pi by 2, 7 pi by 2, you're going to have these undefined values. So basically the graph can't cross them because it can't get there. Okay, but what happens near that asymptote? Well, the graph is either going up to positive infinity or down to negative infinity. So it's kind of a strange looking graph, and it's not all that practical, but you should be able to at least talk about its characteristics, the fact that it's got vertical asymptotes at a period of pi. Also, an interesting thing here, it has no min or max, okay, whereas these ones have a min or max at 1 and -1. Okay, so just know what this looks like, be able to talk about it. These are the key ones, okay, and this is just so you know. You know that cosecant is 1 over sine, so basically how would we create this? We just take the values for sine and take the reciprocal of them and then graph them. And you can also, if I take the reciprocal of these values, there's going to be asymptotes as well wherever sine is 0. So we've got asymptotes all over the place. Same with secant and same with cotan. Cotan looks a lot like tan, but it's kind of going the other way, and the asymptotes are wherever, in this case, wherever wherever the sine value is equal to 0. Okay, so some graphs there to look at, but the key ones are sine and cosine. Okay, some important definitions. Periodic function we talked about. It's a function that repeats itself at regular intervals. It's a very predictable function. You know there's a pattern, and you can go way out and know what the value will be based on that predictable pattern. Sinusoidal is a periodic function that looks like a sine function. So you've heard the expression sine wave. Sine waves you see on the oscilloscopes and things like that, electrical patterns. So it's just a wave that continuously goes up and down. So even though it's called sinusoidal, it comes from sine. Both the cosine and the sine are sinusoidal. Sinusoidal just says the graph is sine-like. Okay, so there's no cosinusoidal. Sorry, there's no cosinusoidal. It's just sinusoidal. Okay, so that's what that means. The period. Now this is a really important thing. The period is how long does it take horizontally before it starts repeating itself. And you can tell that from our table of values. Basically, the period for sine and cosine is both 2 pi. It takes 2 pi radians before it gets back to where you started from. Okay, so the period for both of sine and cosine cosine, sine both have a period of 2 pi. Okay, and the period for tan is actually pi. It repeats itself for every pi units, every pi radians. Okay, couple other things here. Center axis, amplitude, and phase shift. Okay, we'll be talking more about this. The amplitude is, if you look at the graph, it's related to the distance between the middle of the curve and either the max or the min. So in terms of both sine and cosine, the amplitude is 1. So if I drew lines there and there, and there and there, the distance is 1. And the amplitude is kind of like radius. You can never have a negative amplitude, just like you can never have a negative radius. So it's always, it's always positive. Okay. The center axis, I just kind of alluded to that. That's the line, the horizontal line down the middle of the graph. That basically, it's not like a mirror. It's not a reflection line, but it is. It breaks the graph into 2 even parts. So that's an important line for equations. And it's always got the equation y equals something. So the what are we talking about here? Center axis for sine and cos without any transformations is y equals 0, which is the x-axis. The x-axis basically splits the graph into 2 parts. Okay, and then the phase shift. We'll talk more about this later, but the phase shift is really if it's just another word or another phrase for horizontal translation. So once we get into transformations, and if we do shifts or translations left and right for sine and cosine functions, we refer to that as a phase shift. So don't say horizontal translation, say it has a phase shift of. Okay, so these terms are very related to sine and cosine functions. Okay, the concepts here, some of these I've talked about, that these are all periodic functions. They're similar in shape, sine and cosine, have an amplitude of 1 and a period of 2 pi. Now here I start talking about transformations. I'm just going to leave that until we actually do it. But you can see at first glance it's got these same parameters we had for other transformations. It's got the a value in front, it's got the c value that's added at the end, it's got a k value and a d value. So we'll talk more about those in a minute. If you put them all together into one equation, that's where they all fit. So there's the a. So if you remember, the a value was vertical stretch, compression, and reflection. The k value is same for horizontal stretch, compression, reflection. The d is the horizontal translation, or in our case now the phase shift, and c is the vertical translation. So those values all have the same impact on trig functions, so you should be familiar with that. Now, once we get into the k value, you're going to see k. It starts pulling the graph apart, or pushing it together, compressing it, or stretching it. So you can tell that if we did that to our graph, that's changing the period. So there's a direct relationship between the period and the k value. So here's the formula for that. The period is equal to 2 pi, which is the normal period for sine and cosine, but we just divide it by whatever the k value is. And you can actually go backwards too. If you happen to know what the period is, you can figure out the k value. Okay, here's what you need to know about tan function. It has no amplitude because it has no max or min, and it has basically vertical asymptotes at these odd multiples of pi by 2. Yeah, and the period is pi, I think. Did we say that? No. Okay, so that's what you need to know about tan, and that's about it. Okay, so now we're going to get into transforming sine and cosine, and for this exercise, we're just going to be transforming sine. Okay, now cosine is going to be very similar, just different points on the graph, but very similar activity. Okay, So now, since this is my second take, I'm going to try to shorten this lesson by just showing you what I did instead of actually doing it in front of you. So this basically says transform the graph of f of x equals sine x to do these two other graphs. G of x is sine x plus 2 and h of x is sine x minus 3. So this is actually the c value. So c is responsible for the vertical translation. So if c is positive, it goes up that many units, and if c is negative, it goes down that many units. So here's our original graph, and I did compress it so that I could fit them all in one graph. So here's the graph of sine x. Now, whenever I draw the graph of sine x or cos x, you'll see this over and over. So when I actually drew this, I said, well, I want my graph to go out to about here, and I'm going to draw one period or one cycle of my graph. So I actually do this line first, and then I say, okay, halfway between those, that's going to be pi. And then I've broken it into half, and then I break it into quarters. So pi by 2, 3 pi by 2. Now, and you can get this from the table of values as well, but you know that sine starts at 0, and it goes up to a maximum, then it goes down to the middle, 0, and then down to the minimum, back to 0. So there's 5 very critical points all the time. So for sine, start at the middle. So middle, max, middle, min, middle again. So you got 3 middle points and a max and a min. So when I draw my graph, okay, I know where my maxes and mins are. My max is at 1, my min's at -1. So I just do these 5 points, 1, 2, 3, 4, 5, and then I just do a nice smooth curve to make my graph. Okay, and then when I do my next graph, so what happens is for this graph g of x, I'm shifting the whole graph of f of x up 2. So you can think of it as just taking each of these points, these 5 points, and moving it up 2 units. So that went up 2, that went up 2, that went up 2. You can see there's a very defined distance between these graphs. Got my 5 points. Now one thing I did here to make it easier, I actually do a dotted line at x equals 2. X equals 2 is the center axis. So when I do my dotted line there, I can tell it actually makes drawing a curve a little easier. So you can see these two curves, exactly the same shape and length and all that. We just shifted up 2 units or translated up 2. And similar thing for x minus 3. So again, we start with our base graph of sine x, and each point I move down 3. So the y coordinate shifts down 3. And again, I've got my 5 points. And it's always going to be middle, max, middle, min, middle. And I'd already drawn my line in here for the center axis at y equals -3. And then I do my nice curve. And you can see it's very visually appealing. It looks like a kind of a wave. Okay, so that's the C parameter for the vertical translation. Now we're going to look at the A parameters. So the A, if you remember, that's responsible for vertical stretch, compression, and reflection. So I did my axes, and I kind of knew how big I had to make it so that all 3 could fit. So here is my original sine x graph. Okay, so what happens when I have an A value? Well, what the A value does, it multiplies your base points here, the points I drew already, multiplies the y value of each of these by whatever A is. So in the case of g of x, I'm multiplying the y values by 2. So if my point has a y value of 0, what happens when I multiply it by 2? Nothing. It's still 0. And same with that 0, and same with that. So you can see these values are kind of like anchors. But the mins and the maxes are going to change because when I take that point there, it has a y value. It has a y value of 1, multiply it by 2, moves up there. This has a y value of -1, multiply it by 2, goes down there. And then I do my nice sweeping curve. There's my graph of g of x. H of x, the A value is -3. So I multiply these, again, the zeros still stay at 0. Multiply this by -3, so 1 times -3 means the point's down here now, and this point that used to be a min at 1 now becomes a max at 3. Sorry, a min of -1 becomes a max at 3. And there's my graph. Okay, also very visually appealing because of these zeros. Kind of looks like a skipping rope kind of. Okay, so that's the A value. So that takes care of the two vertical transformations, vertical translations here, and vertical stretch, compression, and reflection. So when you have the negative value, I didn't even say the word reflection, but it happened automatically because whatever point I multiply by a negative value, it changes to the other side of the x-axis. So that's where the reflection comes from, is the negative sign. Okay, now we're going to look at the D value. So the D value, that's the phase shift. It's the variable formerly known as horizontal translation. So, and again, you have to be careful with this, right? Because, well, first of all, before I get into there, so I also fit all these graphs onto one. So this graph here, f of x, that's the original sine x. You can see my amplitudes are not changing this time because the horizontal variables don't affect the period. Don't affect the vertical scale. They only affect the horizontal scale. Okay, so there's the original graph f of x. So this graph here, you have to interpret it right. So it's x minus d. So d's value is actually pi by 2. So when d is pi by 2, that means it goes right. So it's kind of like, it's exactly the same as when you looked at the vertex form for a quadratic. You know that it's, if it's x minus 2, that h was 2. Okay, so for this graph g of x, we basically shift everything right pi by 2. So it's kind of better when you see me do this, but just imagine that this is the only graph that's on there now. So what I do is I take each of these 5 points, these key values here, and I shift them horizontally, in this case right pi by 2. So in this case here, that point there, right now it's at 0, I move it to pi by 2. So that point is moved there. This point goes pi by 2, goes across there. This point goes across pi by 2, so it ends up there. You can see every point is shifting, right? So when I actually do my points here, you can see I've kind of got a gap here because this was my leftmost point, so that was my first point to graph. Now what you do is once you've drawn this, you can start using the symmetry and the fact that this graph has, in this case, 1, 2, 3 of these units between important points. So if I go back 3, then this point would be a min since this is a middle. Okay, hopefully that makes sense. Okay, then the other graph, sine x plus pi by 6, that this means d is negative pi by 6, which means you're moving the graph left pi by 6. Okay, so again, I start with my original graph f of x, and I take each point and I shift it pi by 6 to the left. So this point went here, this point went to here, this point went to here, this one to here, this one to here, and then you just join it together. Try to extend it if you can on both ends. Okay, now one thing that's important here is to get a good scale down here. Okay, so I always divide the period out by 4 so I can get my 5 key values. But the phase shift kind of throws a monkey wrench into that because your scale should accommodate that. So in this case, the shift was pi by 6. So originally I didn't have these dots here, I just had the 4 main ones, right? But as soon as I learned, well, I've got to shift this pi by 6, I then said, okay, how do I get pi by 6 here? Well, if I divide this section here, pi by 2, into 3 equal parts, each of these will be pi by 6. And I just continue that on, and then I can see exactly how much pi by 6 is. Otherwise, you're just guessing, okay, and you lose marks if you're guessing on a graph. Okay, so that's the horizontal translation, which is now called phase shift. Okay, so the last transformation is the k value, which is responsible for horizontal stretch, compression, reflection. Okay, so remember, okay, so originally draw my graph of sine x. This time I had to draw 3 separate ones, just because the difference, I didn't want to overlap too much. So there's the original graph. We know sine x has a period of 2 pi. Now, the next graph, g of x, the k value was 2. Now this is important. If you want to get the period, which we do, it's always, period is 2 pi divided by k, which is 2. So the period becomes pi. So in this period here, where we only had 1 period, now we're actually going to have 2 periods, because the period length is only pi. So what I do when I draw this, I still did this out to pi, but I realized, okay, I'm going to have to take this section of the graph and divide it up into 4 quarter sections, and then my 5 key points come there. And then I just repeat it over again for those. And you can see this is a compression, right? You're squeezing, it's almost like an accordion. You're squeezing it together, or a spring. So when you're compressing it, the period is getting smaller. Okay. Now, one way to think about this k value, since it doesn't really, it's not the stretch or compression factor. The stretch or compression factor is 1 over k. So it's compressed by a factor of 1/2. But the 2 value, you can think of how many periods of this can I fit in 2 pi. So you can see I fit 2 of these inside 2 pi. Okay. The last one has a k value of 1/2. So when I go do the period there, running out of room here, when I get the period there, it's 2 pi divided by 1/2, which is really 2 pi times 2, which is 4 pi. So all of a sudden, like with this really long period, so I extended my graph. I only had to do markers at 4 pi, 2 pi, 1 pi, and 3 pi. And then my 5 points still, still are marked a quarter way through the period. Okay, middle, max, middle, min, middle. Okay, and you can see this is actually, it's not, it looks like, since the value of k is 1/2, that it's squeezed, but it's actually the opposite. So it's the factor here is, it's actually stretched by a factor of 2, 1 over k. And again, what I said about how you can interpret that value of 1/2, you could say 1/2 of this period fits inside 2 pi interval. So we've only managed to put 1/2 of a period, which that's what that's telling you. Okay, so you've seen all 4 parameters and the effect they have on the graph. So let's put them all together and come up with a way of pulling information out and then graphing. Okay, so here's an equation, g of x, -2 sine 0.5 bracket x minus pi by 2 plus 7. So this part is only asking what's the amplitude, the period, the phase shift, and the vertical translation. Okay, so the first thing I always do, highly recommend, pull out the values of a, k, d, and c. That's the way they appear in the equation. The d comes before the c. It's not all alphabetical order. Okay, so the a value is -2, the k value is 0.5. The d value, remember it's x minus d, so d is actually positive pi by 2, and c is 7. So let's get to work. So the amplitude, remember I said amplitude is always positive. So you take the absolute value of a, which is absolute value of -2, so the amplitude is 2. And then let's look at the period. So we've seen this before. Period is 2 pi. Now it's actually divided by the absolute value of k. That's just in case k is negative. because again, period has to be positive, just like amplitude. Okay, so in this case, k was already positive. 2 pi over 0.5, that's like 2 pi divided by half, which is the same as 2 pi times 2. So the period is 4 pi, and I put radians instead of units. The vertical shift is just your c value. So since c is positive, 7 units up. And the phase shift is your value of d. So that's pi by 2 radians. And since it's positive, it's to the right. So remember, you have to add these directions when you talk about the phase shift and the vertical shift. Okay, the second question is, now that we've got this, is to graph it. Okay, so I've got a pretty good strategy here for you. So pay attention. So I'm already assuming we've got these values up here. We already know the period's 4 pi from above. The center axis is just the c value. So it's y equals whatever c is. So it's y equals 7. That's basically the line down, horizontal line down the middle. And then this is actually pretty cool for graphing, because for the vertical scale, you take the c value, which is your center axis, and you add and subtract your amplitude. So we've already got the amplitude is 2, not negative 2. So it's it's 7 plus 2 for the maximum value, 7 minus 2, 5 for the minimum. Okay? So let's use that information now while it's still fresh in our mind. So whenever I graph a sine or cosine function, the first thing I do is I draw this, sorry, let me move this up for you. I draw this sideways T graph like that. Okay, so it's all blank, just imagine it's blank. First thing I write in is beside the line is I write the value of the axis of symmetry, 7. And then I know the max is 9, so I put the 9 up here, put the 5 down here. Now, you notice, I didn't put a 0 here beside there. I'm not calling that the x-axis. I'm calling it the what am I calling it? The center axis. Yeah, there it is. That's the center axis, which could be any value. Okay? I see a lot of teachers in textbooks, they insist on drawing that solid line at x equals 0, but it really makes no sense. What if you had your axis, your center axis at, say, 120? So your graph would look really, really strange. So the first thing we do is we build our vertical scale. Got our c value there, c plus amplitude, c minus amplitude, and we're good. Okay, the next thing we do is we look at the period. So again, we knew the period was 4 pi. So I said I want my graph to go out to here. So I drew my 4 pi here, cut it in half, drew my 2 pi, made my mark for pi and 3 pi. And then what I did was I looked at the graph. So in this case, so the graph is sine, but it's really negative sine. Yeah, it's really negative sine. So instead of the graph going from the middle to the maximum and back down, it actually goes from the middle to the minimum. Okay, and that gets you your pattern right away. So you can see the next thing I did after I did my scale and figured out it was negative sine, so it's going to go in this direction. So I did these little points here. So there's a point, there's a point, there's a point. So there's my 5 points. So if I didn't have any phase shift, that I would be done. That would be my graph. But there is a phase shift. So I don't bother. I only want to have one graph. I don't want to have a series of stages of the graph. But I do put these points on, so it's easier for me to do the last step. Now the last thing we want to do is the phase shift. So the phase shift was pi by 2 to the right. So again, we take each of these points and I make another point pi by 2 directly to the right. So in this case I drew a little box. Okay, so that's my new point. There's my new point. There's my new point, because that is pi by 2, right? Okay, and then this goes here, and then this one, I just made a little extra room to go here. And so then I've got these 5 points. I draw a line to connect them. And then what I do is I actually said, well, I'd like to fill that in. Where would the next point to the left be? So I know that the next key value is going to be, let's see how it works here. It's going to be 2 values from where this one is, 2 to the left. So 1, 2. So I know I'd have a maximum there. Sorry, I guess you can't see that. So I know I'd have a maximum there. So I just kind of roughed this in. And, you know, you could draw a solid line there, but I didn't want to mess up my scale here. So at that point I just drew a dotted line, but I put a solid line in here to make my graph appear more realistic. Okay, and a lot of times when you do a graph, they'll tell you, draw your graph from 0 to 4 pi. So if you'd left off this little section here, well, you didn't totally follow the instructions. So if it just says to draw one cycle of the graph or one period, well, that's what we did. So we could get away with just drawing this section. Okay, but sometimes you have to extend it so that you actually draw the interval that was asked of you. Okay, let's try. This time it's telling us in words what's happening to the graph. This time we're working with cos x, so it's transformed to g of x, the new function, such that g of x has an amplitude of 4, a period of pi, phase shift of pi by 6 to the left, and a vertical translation of 2. So you're probably reading this and going, well, that I know what these values represent, so let's go through them. It tells us the amplitude is 4. Okay, so remember, amplitude is the absolute value of a. Okay, so a could actually be 4 or negative 4. So let's just leave it at 4 here. You could put a little question mark. I think I came back to this and wrote a 4 later. The period is pi. So if we're going to make an equation, which we've been asked to, we're going to write the equation and make a graph. I got to convert the period back into k. So it's actually almost the exact same formula. Instead of period equals 2 pi over k, it's k equals 2 pi over the period. So 2 pi divided by pi is 2, so the value of k is 2. Phase shift is, it says pi by 6 radians to the left, so that the phase shift is negative pi by 6, and that's what d is. Vertical translation of 2 up, so the up tells you it's a plus 2, and that's your c value. So right away you've got your a, k, d, and c. Now, we're starting with cos x, so going back to this, a would be negative 4 if there was a vertical reflection, but there's no mention of that here. So because there's no vertical reflection, we know it's 4. If they'd said vertical reflection, we would have made that a negative 4. Okay, and now we just go ahead and plug it in. Okay, this is from your template formula. So the a is 4. You put your cos in because you know it's a cosine transformation. The k value is 2. Then your x minus d, so x minus negative pi by 6 is plus pi by 6. Make sure you've got all the brackets there, and then a plus 2. Okay, so we've got our equation, and let's just go directly from the equation now to graph this. Okay, well, we're going to use the period from before. That's probably the only thing. Okay, so when I'm graphing this now, the first thing I'm going to do, I love to do the vertical scale first and then the horizontal scale. So the vertical scale, the middle of that's going to be 2. So the center axis is y equals 2. The maximum is c plus the amplitude, 4, 2 plus 4, and the minimum is 2 minus the amplitude. So you know 6 and negative 2 are your max and your min, and the 2 is your center axis. So fill those in. Okay, and it always works out really nicely. You're not guessing and getting it wrong. Okay, the period was pi, and it also said, by the way, kind of glanced over this, graph it over 2 cycles. Believe me, there's nothing worse than drawing an excellent graph and then going back and realizing they asked for 2 or 3 cycles and you just filled up your page with 1. So it means you have to start over, at least the horizontal part, or you know you're going to lose some marks, probably 1 mark. Okay, so back to the graph. Now we do our horizontal scale. So it does say 2 cycles. So I'm going to have to fit in 2 periods. So each period is pi. So when I made my scale, I started at 2 pi, cut that in half to get pi, and I know there's a cycle in each one. So then I subdivide each of these into 4. Okay. Now, since a is, so the function we're going to start from is just cos x. It's not negative cos x because it's plus 4. So cos x always starts at the maximum, goes to the middle, down to the min, and then back up to the maximum eventually. So when I do my points, so if I do my interval here to here, so I start at the max, quarter of the way through is my middle, halfway through is my min at pi by 2, and then, so where's the next one here? Then this is back to the middle and back to the max. So these 5 points are my graph without the phase shift. So I put the points in there, so I'm ready to do the phase shift to the end. Then I do the same points here. So starts there, then down, sorry, where are we? Starts there, down to the bottom, back to the middle, back to the top. So those are the, I forget how many points it was, 9 points I think. And then what I do is I do my phase shift. So the phase shift, pi by 6 to the left. Now, here's the problem. I have to make sure I know what pi by 6 is here. So I actually divided this. So pi by 2, I divided it into 6s. Or pi by 4, I divided into 3s. So each of these I divided into 3. And that works out so that there's actually 12 of these intervals for pi. So each of these is pi by 12. And that works out well because pi by 6 is really just 2 pi by 12s. So that means I'm going 2 units to the left. So I take each of these points, start with that one, move this one 2 over, move this one 2 over, everything goes 2 to the left. You can see, now this time I didn't do my squares, but I managed to keep track pretty well. And then we just connected the new points like that. Okay, and you can see I did do 2 cycles because I went from here, that's 1 cycle, and then 2. I actually went a little bit more. Okay, so that's the process for, well, in this case we started with a description, we developed the equation, and then we graphed it. Okay, so a couple more pages. This will be a lot shorter than the original, thankfully. Okay, so now that we've covered how to graph, again, you're going to have to practice this with the homework for sure. Now it's a totally different skill if I give you a graph and say, hey, what's the equation of this graph? Okay, so that's what this section's all about here. So I'll give you some really good pointers. Hopefully you'll apply them. You can actually make this a fairly quick process. Okay, so when you get this graph here, you don't really know where to start. So I would suggest the very first thing you do is you point out where the highest and the lowest points are and put dots where those are. So I've actually got 2 maxes and 1 min. Okay, and so I've got some formulas up here. I can actually get the amplitude and the C value by using the maxes and the mins. Okay, so to get the A value, or the absolute value of A, the amplitude, we take the max, subtract the min, and divide by 2. So here's my calculation here. So the amplitude is 5, because the max is 5. 5 minus 1, so that's basically the difference between the max and the min. and then I divide it by 2 because the amplitude is really half that distance. So the amplitude is 2. Then to get my c value, the middle, it's a very, very similar formula, except instead of subtracting them, I add them. So 5 plus 1 divided by 2. So that's the average of the max and the min. Okay, 5 plus 1 divided by 2 is 3. Okay, so already I've got, 2 of my values almost. And then what I do with these, this is usually the hard part for most students, is how to calculate the period. Some students will try to figure out from the middle, and that's really a bad idea, because your period will cross through here several times. But if you remember, if I go from one max to another, or one min to the next one, that's one period. Okay, so I look at my graph and I say, well, I've got 2 maxes, I've got 1 min. So I can't really work with the min because I don't know where the next one is, but I can figure out, I know I have a max at 7 pi by 2. I have another one before at negative pi by 2. So what's the distance there? So I would recommend actually subtract them like I did here. So the period is 7 pi by 2 minus negative pi by 2, which is really plus. So that works out to 8 pi by 2, which is 4 pi. So the period is 4 pi. Now we can get our k value. K value is 2 pi divided by the period, which is 4 pi. So that the pi's cancel out, so k is 1/2. Okay. Now, if you notice, I've got the k value, I've got the c value, I've got the a value, at least the number part. What I don't have is, well, what function am I going to use? Am I going to use sine or cos? So this is important. You actually have 4 graphs to choose from. You may think I've only got sine and cos, but you've got sine, you've got negative sine, you've got cos, and you've got negative cos. So it's important, hopefully you can see this in the corner, it's important to remember what these shapes look like. So sine starts in the middle, goes up. Negative sine is a reflection, so it starts in the middle, goes down. Cosine starts at the top and obviously goes down. And negative cosine starts at the bottom, goes up. So what I would recommend is go back to your graph. Now you got to make sure you're looking at the right place. So this is the y-axis here. Okay, so what graph does this remind you the most of? Or at least, it might not be exactly, but what's it close to? So I would say probably cosine, because it's pretty close to the maximum. Now, I forgot to mention here, the question's asking for 2 equations of the function, one using sine and the other using cosine. So we really have to pick 2 of these. Okay, so let's start with, well, I wrote down the sine ones first, so let's do that. So the first thing you do, does this look more like sine or negative sine? And the fact that it's heading down when it begins tells me it's probably closer to negative sine. Okay, so I'm going to start with the negative sine. So what that does, now I didn't write a lot of information here, it's mainly about talking. Okay, so the fact I'm using negative sine, well, that goes back to the a value. So even though I wrote a was 2, it could be negative 2, and in fact it will be if I use negative sine. So I now know that a is negative 2 and sine. Now the only thing I don't know now, I know the k value, I know the c value. The only thing I don't know is the d value, and you actually don't know your d value until you picked your base function to start from, because you don't know how much you should shift it. So let's look at the sine value. So negative sine, I'm going to highlight that point there. I actually forgot to mention, I like to draw a solid line through the axis, through the center axis, so I can really see, okay, if I'm talking about sine or negative sine, I know that this is the middle of the graph, and normally negative sine would start here. Okay, it would start at this value here. Sorry, negative sign would start here and go down. Our graph starts here and goes down. So what did we have to do to this point to turn it into that point? Well, we had to phase shift it pi by 2 to the right. Okay, so that tells you your d value is pi by 2. So now I know the d value, so it's x minus d, so it's x minus pi by 2, so that fills in the missing piece of information. Okay, let's go to the next graph. So the next graph, we don't have to redo all this. We know the k value, the c value, and the absolute value of a, the amplitude is the same. We just have to pick, are we going to use cosine or negative cosine? Okay, and we already talked about that. Cosine starts at the top. So this looks more like cosine than negative cosine. So I put asterisks beside the two that I was going to use. So if I use cosine, okay, normally cosine would start here and go down, because that's the max, and that's, you know, the y-axis. It would start there and go down. Our graph starts here. So what do I have to do to this point to turn it into this point? Well, this time I'm shifting it pi by 2 to the left. So d is negative pi by 2. Okay, so I'll plug that in right now. So if d is negative pi by 2, it's x plus pi by 2, because it's x minus d. These two values are exactly the same. We're using cosine, and the fact that I'm using positive cosine, not negative cosine, means that sorry, we weren't seeing that. So there's your phase shift. D is negative pi by 2. Your k value stays the same. Your k stays the same. C stays the same. The amplitude's the same, but this time we're not using a negative cosine graph. We're using positive. So there's your equation. So if you look at it, it's kind of interesting that you can come up with two equations. You can actually use all four of these if you wanted to, and in fact you can actually go even farther. You could, when you do your phase shift, you could, you might not go to the nearest point. You might decide, oh, I'm going to shift it all the way, to the next period. So there's actually an infinite number of equations. I mean, in practicality, there's like 4, maybe 8. So there's lots of equations that create the same graph. If you plug these equations into Desmos, it's exactly the same graph. So it's an interesting relationship, because a graph can have multiple equations, but an equation can only have one graph. Okay, so keep that in mind. All right, last page. So we're going to look at an application question and see what they're asking here. So the Roundup is a popular ride at many theme parks. It consists of a large wheel that starts in a horizontal position. As the ride picks up rotational speed, the wheel tilts up to an angle of about pi by 4. You can see I've already written something there. We can pretend we didn't see that yet. Determine a sine function model for the vertical position h in meters of a rider on the Roundup after t seconds, with the following specifications. The maximum height above the ground is 7.5 and the minimum height is 1.5 meters. The wheel completes one turn in 5 seconds. The model predicts the highest point at t equals 0. So that basically means you'll have a maximum height at 0 seconds. Okay, so even though I've already done the work here, I want to talk about how I created it. Okay, so I always start off, this is a really good idea. So here's a model of the ride, circle going around and around. So I've got the circle, and right beside I drew this vertical part of my graph and then my center axis along there. So then I start reading the information. It says the maximum height above the ground is 7.5 meters. So I went ahead and wrote in my 7.5 meters there. So it applies to the top of the ride as well as that point on the graph. That's how these line up. And then the minimum height was 1.5. Okay. Now to get remember the formula we used to get the C value? you add these two values together and divide by 2 because you're averaging. So there's where I calculated C. 7.5 plus 1.5 is 9. Divided by 2 is 4.5. So I got my vertical scale. So now I move to my horizontal scale. So this is a different situation because usually this axis is to do with the angle as it goes around. But this time it's based on time, which is a little more practical for application questions, I think. So we still start off with the same thing. We write the period down. It says it's 5 seconds. Completing one turn means that's the period, or one cycle. So how do I get the k value? Well, it's 2.2 pi divided by 5. So when I simplify the 2/5, that's the same as 0.4 pi. So you'll notice the k value actually has a pi in it because the period did not have a pi in it. It doesn't cancel the pi on the top. Okay, so there's my k value. The a value, basically subtract these two and divide by 2. So, well, you could actually just calculate that distance. It's 3. There's the c from before. Now, we choose what function we're going to use to model this, and it's pretty obvious. Starts at the top, goes down. That's going to be cosine. Don't forget we're using t as our variable. It tells us that up at the beginning. So it's going to be h of t as our function instead of x's and y's. Okay. Now if we use cos t as our base, that's good because we don't require a phase shift because it's starting exactly where cosine starts. So no phase shift means d equals 0, and then we plug in back to our equation. Since we're using cosine, not negative cosine, that 3 value for a stays at 3. Cosine, because we're picking cosine, and then the k value 0.4 pi times t. You don't have to put it in brackets, but I like to separate them. A lot of time when you're doing these equations, you'll see the pi there and you'll forget to write the x or the t. So be careful of that. And then there's no d value, so it's just t in the brackets. And then plus 4.5. So that's the equation that models this. So that's it for today. A long lesson, covered a lot of material, but hopefully it resonates with you. But for sure, you're going to have to practice the homework. The homework solutions are available, so try the questions out and then check your answer to see if you got it right. Don't immediately go to the answer and say, oh, yeah, I could have got that. Because when you see it on a test, it's a different story than watching someone do it on a video. Okay, so there's the assigned homework. Please work on that. And our next lesson will be working at solving trigonometric equations, which is a brand new topic. A lot of similar strategies as we used with polynomials, solving polynomial equations. Okay, so that's it for today. Hope you have a great day, and we'll see you on the next lesson.